my screen. So if I move to
can see
slideshow, can everybody see my screen?
Yes.
Wonderful. So thank you very much. As you've just heard, I'm Dr. Phil Wiseman. I'm a researcher at the University of Southampton. Forgive me, I'm not actually in Southampton at the moment. I'm in North Devon, so I'm waving over at the people in South Wales. I can see Wales over the water, and waving up the Bristol Channel as well to the folks in Bristol. How did I get to Southampton? I actually grew up in near Gloucester, so not too far away at all, and studied my undergraduate in Durham, moved to Munich for a PhD, and now found myself in Southampton. For the last four and a bit years in Southampton, I have researched supernovae. I'm going to take you on a little tour of supernovae, exploding stars, and leave the bits that remain to the other speakers later in the day. So I'm going to start by casting our minds back 4,500 years or so. I say or so, plus or minus 1,000 years BCE. So in astronomy, plus or minus 1,000 years, we count that as being extremely accurate and precise. You know, that's a really good job. Somewhere in Kashmir, Buzahama in Kashmir, and imagine you are a hunter and you decide you're going to carve on a rock extremely special scene that happened. So you carve yourself with your spear, you carve your fellow hunter with a bow, you carve the stag that you are hunting. But there was something particularly special about this particular hunt that you went on, because not only was there one bright object in the sky, the sun, but in the daytime there were two bright objects. And so you carved this on your rock. People think that this is the first time that humans, or humans as we know it, saw and recorded a supernova explosion, something that was so bright it was visible in the daytime. Now, of course, this could be completely wrong. That could have been just a poor representation of the moon, but it's something worth speculating over. So let's fast forward nearly 5,000 years to the Book of Han in China. An entry in the Book of Han reads, in the second year of the epoch Zhongping of the 10th month on the day Gui Hai, a guest star appeared in the middle of the southern gate. The size was half a bamboo mat. It displayed various colors and gradually lessened. In the 6th month of the succeeding year, it had disappeared. So that's understandable. Things appear and disappear in the night sky all the time. They can be comets, asteroids, planets, of course, change around in the sky and appear and disappear. But what was interesting about this particular object was that it stayed in exactly the same position. Comets and planets appeared and would move before disappearing. And so we believe, again, that this, again, was a supernova. Something so bright that it appeared as new in the sky. Another 1,000 years onwards, and something is observed across the world. It's observed in Japan, in China. It shone so brightly that objects on the ground could be seen at night. That means that this object was casting a shadow, potentially. In Iran, they say that the color changed with time. You wouldn't expect that with a planet. It was seen in Iraq, it was seen in Egypt, and in Egypt they said it was nearly as bright as moonlight. So if you think about, you look at in the night sky, that's something as bright or brighter than Venus, the second brightest thing in the night sky. So this is another extremely bright new object. It was also observed in Europe, and once more was recorded on rock carvings here in New Mexico. Then we start to get some more frequent observations. So in 1054, in the Book of Song, there was recorded the coordinates, the very specific coordinates of the explosion that happened there. And this, if you go and look there now with your telescope, and this can be seen in relatively beautiful nebula, which we know as the Crab Nebula. And indeed, there's a pulsating source in the middle of this, which Nils and Diego will be able to tell you a lot more about, which we believe is the remnant of that supernova explosion that happened in 1054. Again, we're going to fast forward maybe another 800 years, and something very important has happened in those 800 years. That's that humanity has discovered and invented telescopes. So now we're not looking at things just with our naked eye, but we're looking at them through telescopes. These were seen by Ernst Hartwig in Estonia, Ludovic Gouly in France, and Isaac Ward maybe in Ireland. Object being just in some unknown new patch of dark sky. And this brand new bright object was seen in Andromeda. Now, Andromeda in the 1800s was thought to be a nebula. There were plenty of nebulae that were known. They'd been catalogued by people like Messier. And it wasn't really known what they were. Nebula kind of just means cloud, right? But this object appeared, S Andromedae appeared in Andromeda, and was first detected with a magnitude of around 6. Now, magnitudes for the uninitiated are complicated things that needn't be so complicated. We are astronomers after all. And so the fainter something is, the higher its magnitude. So you will often see magnitude diagrams drawn where the numbers increase as you go lower. That means that the object got fainter as the magnitude got higher. And you can see here that S Andromedae declined nearly 6 magnitudes over the course of 2 or 3 months. Now, I'm not going to do the calculations, but that means it faded by about 150 times. About 150 times fainter over those 2 months. Okay, great. So one happened in a nebula, and over the next few years, more and more was seen, and a lot of them appeared in nebulae. And that became extremely interesting in the early 1900s, when astronomers such as Fritz Zwicky started looking at these nebulae, and of course, Hubble and Swan-Leavitt and many famous early 20th century astronomers who started to work out that these nebulae, once they could measure the distances to them, were not clouds within our own galaxy, but were separate galaxies themselves. They were much, much further away. Andromeda being. Now, if we look back at this visual magnitude of S Andromedae, this new star or nova, we find that to have a magnitude this bright, so 6 is just about visible with the naked eye in a very dark sky, to have a magnitude this bright, but when you're in a different galaxy, you must have an extremely luminous object. S Andromedae must have been so bright that it was almost as bright as the Andromeda galaxy itself. To create such intense luminosity, you needed an extreme explosion, not just a nova, like many of these flashes had become known, but this is what Fritz Zwicky thought of the expression supernova. These were done at the Palomar Observatory in the USA. And then the next breakthrough in 1941 coming from Rudolf Minkowski, who from Mount Wilson didn't just observe the photons through the telescope and record how bright they were, but he also split them up. So if you take something like a prism, like Pink Floyd did, you take white light coming in, you split it up, and you can see the different intensities at different wavelengths. That's what we call a spectrum. This technique is called spectroscopy, and it can allow you to see the composition of the source that is creating the light. So Minkowski observed several supernovae in different galaxies and noted that his observations indicated two types of supernovae: a very homogeneous group called type 1. Homogeneous here meaning they all look very, very similar in their spectra. And 5 different objects that looked distinctly different, which, because we're astronomers and we just use the simplest thing we can, he called type 2. So we have one set of objects called type 1 and one called type 2. And over the next few decades, we observed more and more. We got different spectra and more light curves. And eventually more like 4 categories began to appear. So on the top here, you have one that we call type 1a, in the middle, type 1b, on the bottom, type 1c, and then in the pink here, we have type 2. You can see where this is going with the typing, right? And so all these types are based purely on what the object looked like, not what they are or how they're created. So they're phenomenological. And from the 1980s up until now, we've effectively just spent most of our time dividing these groups into smaller and smaller and smaller groups that look very slightly different from one another. But why do they look the way they do? What are these bumps and wiggles? Why do they go up in the left-hand side, which is the blue short wavelengths, and down in the red wavelengths? And what are these big peaks in type 2? Well, let's go and have a deep dive into the actual physics and find out. So the actual spectrum of a type 1a supernova should look a bit like this thick green line, okay? This is what we call a black body spectrum. That just means something that is a perfectly thermal emitter of radiation. So it's just something that is extremely hot, is a perfect absorber and a perfect emitter. And because it's hot, it peaks in the blue wavelengths here, and it's a bit fainter in the red wavelengths. But what we actually see is the thinner green line here with all these bumps and wiggles. Well, that's because of chemistry. There are lots of different elements and ions that happen in space and in supernovae. And the electrons in those ions have this very specific energy levels. And if a photon hits one of those electrons, it can jump an energy level. Jumping that energy level has a very specific wavelength, a very specific energy, which corresponds to a very specific wavelength. And so that photon can't make it through as part of the green line, gets absorbed, and you end up with these dips. They happen at very different, very specific wavelengths for different elements. Now, fortunately, we've had people on Earth who have tested these in the lab, and so they know the wavelengths of those lines for different elements. So here we have, for example, a big dip for calcium. We have very distinctive silicon dips. There's lots of iron in type 1a supernovae, lots of magnesium in type 1a supernovae. And you'll also find sulfur. These are really distinctive, and you don't see these in some of the other types of supernovae. So if you see particularly these silicon features, and it's happened to many of us, where you get a spectrum through, you see the silicon dips, and you say, I know this is a type 1a, it has very strong silicon. But why iron? Why silicon? Why not hydrogen or helium? These are the most common elements in the universe. Why is there no hydrogen or helium in the type 1a supernova spectrum? Well, to answer that question, we have to go and look at how stars evolve. So taking a look at a sun-like star, and please excuse my relatively simple Microsoft PowerPoint diagrams. There are two main forces happening in a star. A star, being a big ball of gas, has a lot of gravity. It's very, very heavy. The sun is 10 to the 30 kilograms, 30 zeros. That's a lot of kilograms. And so all of that mass means there's a huge amount of gravity pulling all of that matter together, bringing it in. So the star should just keep on collapsing and end up as a very, very small ball. But it doesn't. In the middle, the density gets high enough, as we were hearing earlier, such that once it's so dense and hot that hydrogen ions can begin fusing together. Once they're hot enough and they fuse together, they create helium. But at the same time, we find that the state of helium is actually more favorable energetically than individual hydrogen ions. And so you create your helium. This radiation, which is extremely intense, streams out from the middle of the star and actually exerts a pressure on the rest of that plasma. And so you have gravity pulling in, you have radiation pressure pushing outwards, and your star lives very happily in this balance we call hydrostatic. And a star about the size of the sun can do that for 10 billion years or so. But at some point, like any object that is burning or fusing fuel, it will run out of fuel at some point. In the center of the star, you will deplete your hydrogen, so you can't fuse anymore into helium. And so the fusion reaction falls away. Gravity is the only force left. And so gravity wins. Gravity contracts the star, but when it contracts the star, you do get enough heat in the center, you get enough density in the center of the star that you can now start to fuse your helium. So now the helium is fusing, and the helium fusion creates carbon, but it's also energetically favorable and creates some radiation that then expands the star again. But this time the fusion is happening at a much higher temperature. The higher temperature means the radiation is more intense than it was for the hydrogen fusion, which means that the star expands to be even bigger. Because it expands to be even bigger, the outer edges are much cooler, so it turns red. In astronomy, blue objects are hot, yellow objects are in the middle, and red things are cool. So you have this massive, cool red object, which we know as a red giant. This is this phase we think Betelgeuse is in at the moment, with helium fusion happening in the core. And you'll notice this red shell around. The star can get so big with so much heat coming from the middle that you have very extreme stellar winds. And those winds can basically blow off all of the outer layers. The leftover hydrogen, the leftover helium can be just blown off into space. Eventually, of course, that helium will run out. You have no helium fusion anymore. And so you contract. But this time, the contraction, you never reach the temperatures that you need to burn or fuse that carbon. So you end up with what we call a white dwarf. The star contracts so far that it's extremely dense, that the only thing stopping it from collapsing even further is the fact you can't push the electrons any closer together because of some fundamental, it's called particle physics, which we call electron degeneracy pressure. Okay, so you have a white dwarf, it sits there, it's very, very massive for the size that it is. So it's about the size of the Earth, but about the mass of the sun, maybe a little bit less. And it's very, very stable. A white dwarf could just sit there for many, many years, billions and billions of years, until the universe kind of did whatever it's going to do. Aha. But it would only do that if it's on its own. What we know, however, is that most stars, about 50% of sun-like stars and 80% of more massive stars, live in binaries or larger stellar systems. So you could, for example, have a white dwarf living next to and orbiting another red giant star, which is undergoing its helium fusion, its radiation and carbon being the waste products, and of course those stellar winds. So you might have the scenario where the outer edges of that star can actually be transferred onto the white dwarf, making it heavier and heavier and heavier. That makes the white dwarf actually get smaller as things get even closer together, much hotter and much denser. Another thing you could do is you could have two white dwarfs in the same system. They could get closer and closer together. While they do that, they actually radiate gravitational waves, and I will defer to Vivien's talk on gravitational waves. They get closer and closer together until, again, you might be able to transfer mass between one or the other. Eventually, you reach a point where there is enough temperature and pressure that the carbon burning can begin. But instead of having a nice convective plasma, you have degenerate matter. It's so close together that once you ignite one or two atoms of carbon, you start burning the entire star in an instant, which we call a detonation. The star effectively instantly fuses all of its elements to much, much higher mass elements, and you have a supernova explosion. I'm going to show you here what one looks like. So this will start potentially in the core of the white dwarf. This blue thing here is the white dwarf, and this kind of flame pushes out the edge of the star and then will envelop the white dwarf as it then expands and explodes off into space. Whilst it's doing this, it's bombarding all of that carbon with neutrons. It's fusing them into much higher mass elements like magnesium and sulfur and silicon and lots of nickel. Nickel being the highest mass element that you can fuse before it's not energetically favorable anymore. So this is effectively how the type 1a supernova happens, and this then will blast off into space, showering the galaxy with all these new elements that it's created. I'm gonna just try it. Now we have a supernova. We have a very, very rapidly expanding fireball, 10,000 kilometers per second it's expanding at. And as I said, it's created a huge amount of nickel 56, is a very particular isotope of nickel, which is the highest part of this curve of energetic favorability. This nickel 56 is radioactive. And so this plasma, as it's expanding, is absorbing gamma rays as the nickel 56 decays. These gamma rays, again, extremely energetic. They interact with the plasma, which absorbs them, and they radiate thermally. Thermal radiation, as I said before, is how you create a black body. And so that's what causes the supernova to look like it does. So we have all our elements from the spectrum, and we have the shape of our spectrum from this thermal radiation caused by the gamma rays from the decay of nickel 56. So what does one of these look like? What does this type 1a supernova look like? Well, I'm going to show you one. This isn't one that you could have observed with ancient Chinese observers or even 19th century telescopes. It's one that you need a 250 megapixel camera on a 4-meter telescope in the Atacama Desert, because it's 2.6 billion light years away. This one was called DES 13C1JUW, part of the Dark Energy Survey, which is a survey, the time on that searches the southern sky for supernovae. And so this is what we'd see in the sky, lots of different things wiggling around. And the colors here are just different colors of light. And then boom, the thing goes up, it gets much brighter, and then fades away again pretty quickly. And then after maybe 50 or 60 days, 70 days, it becomes almost consistent with what it was before. So it's up for maybe 2 months we've got to catch these things. So I'll let this go again. You'll see it wiggle around. This is just us not really knowing how bright that part of the sky was. And then suddenly, boom, gets bright, bright, bright. You'll also notice that at the peak there, the blue is much higher than the red. But later on, the blue declines much, much faster than the red. That is the supernova getting redder or the supernova cooling down. As it expands, it becomes much, much less dense and much, much cooler. And so we see it get redder. And that's another classic characteristic of type 1a supernova is you see it cool over time. Just show that one more time. In total, in the dark energy survey, we have about 2,500 type 1a supernovae that look like this, and they push all the way out to 5 or 6 billion light years in distance, or redshift of about 1 for those who get the notion of redshift. That's really important. Type 1a supernova are very, very useful objects for us, and that's because we can see them so far. So if you look at this diagram here, I've plotted redshift on the bottom. Now, the concept of redshift can be a bit tricky, but it's basically the same as the Doppler effect. The further something is, the faster it's moving away from us, and so the redder its light gets stretched. On the y-axis here, I just have the peak magnitude in the blue of the supernovae. And you see the relation here. The faster something's moving away, i.e. the higher the redshift, the fainter the peak magnitude. So the further something is, the fainter it is, and the further something is, the faster it's moving away from us. That means that type 1a supernovae are very, very good indicators of distance in the universe. We can then use them to measure how fast the universe is expanding, a very important question for the fate of the universe. I say they're very, very good. We'll all follow the exact same line up here, but they don't quite. You can see that there's quite a lot of scatter. They're not all focused on one straight line. So we actually then do our typical thing in astronomy and find some other correlations that we can use. On the left here, again, we've got the peak brightness of the supernova. It's correlated with the color of the supernova. It turns out that bluer supernovae are brighter and redder supernovae are fainter. So we can correct for that. If we see the supernova is red, we can add a little bit of brightness to get its actual peak brightness in the standard sense. The same for the time it takes for the supernova to evolve. Things that take a long time to evolve are a little bit brighter than things that take less time to evolve. We can correct for these, and when you correct for these, you find that actually they follow a much tighter relation. And you can fit a line through this relation of the universe and measure certain parameters. For example, the Hubble constant, which tells us how fast the universe is expanding and is subject to serious debate at the moment. You can also measure things like the density of dark energy, which won the Nobel Prize in 2011. So type 1a supernovae become extremely useful tools in cosmology. Okay, great, but type 1as aren't everything. The other things explode in the sky. So I'm going to very quickly mention some of the other ways you explode a star, like in the type 1b and c supernovae and the type 2. So type 2, let's start with type 2. What do they look like? Well, their spectrum has very, very prominent lines of hydrogen. To work out where those hydrogen lines come from, we have to go back to our little diagram of a star. So this one, instead of being about the same size as the sun, is more like 10 times the mass of the sun and only 100 million years old rather than billions of years old. When it becomes a red giant, it does exactly the same as the previous one did. The sun-like star falls in on itself, but this time, instead of becoming a white dwarf, it gets hot and fuses oxygen, this time creating silicon. It does the same with the silicon once the carbon and oxygen has run out. But this time, eventually you end up creating nickel. And as we said before, nickel and iron, you can't fuse them at all. It becomes impossible to fuse them with themselves because you can't get any more energy out. So eventually you start building up this dead core of iron and nickel in the middle of your star. The nickel itself decays to iron, as we showed earlier. Eventually, that becomes too heavy. The degeneracy pressure can't hold that up anymore, and that core collapses. Collapses in on itself at close to the speed of light. Eventually gets held up by neutron degeneracy pressure. So not the electrons, but the neutrons, you can't push them any closer together. We'll hear a lot more about that later on. When you get this neutron star and lots of other material is falling onto it as the core is collapsing, you have an extremely high flux of neutrinos come streaming the other way. And somehow, and even in 2021, we don't really know how, these neutrinos manage to take this collapsing center of a star, turn it the other way around, and blast it out as a supernova. So a type 2 supernova will be one where there was still some hydrogen left. You'd never had quite enough stellar wind to get rid of all of this hydrogen. So you get these very strong lines of hydrogen. And you're likely to leave behind a neutron star and maybe in some cases a black hole, but we don't think that happens because you probably wouldn't see this supernova at all. These type 2s, we think, but they're quite a lot fainter than type 1As, and so you don't see so many of them. What happens if, when you did all of this core collapse and the neutron star creation, you didn't have a hydrogen envelope, but you only had a helium envelope, or you had no helium envelope, but you only had the core left with no envelope at all? Well, that's when you get a type 1b with helium or silicon coming back in the type 1c. Now, that's a kind of very basic overview. There are actually many more subtypes, and they get to confuse us a lot. I'll show those in a couple of slides' time, but just here I'll show you how many of these supernovae we've seen since the first telescope started seeing supernovae in the 1800s. You can see in 1930s, not that many, but we started to get more and more, maybe up to 100 by the 50s. And now notice the y-axis here changed to a logarithmic scale. These dedicated supernova searches came online. And then once we get to the noughties, instead of pointing at individual galaxies, we were pointing all over the night sky every single night, and you were able to detect thousands and thousands. That will go around on the loop again. So early in the century, to detect supernovae, you'd have to point at individual galaxies, go back to them again and again, and see something new. That's not very efficient. So later in the century, when we could get our nice big wide area cameras, survey the entire sky every few nights down to very deep magnitudes, we see what's new there, and everything suddenly builds up. So now it goes from 1,000 in 2000 up to close to 30,000 in 2020 as all these new surveys came online. So that's the current state of play. And I'll point out that this is just confirmed supernovae, not total supernovae. We've seen lots and lots of things that we never managed to get a spectrum of So we never managed to confirm that it was a supernova or what type of supernova it was. So with all of these modern surveys that have got us these huge numbers in the last decade or so, instead of just our type 1As, type 2s, and 1BCs, we have a huge plethora, a zoo we call, of transients. We're very inventive, so we call them like the supernova that they look like, 91Ts, 91BGs, supernova 1AX, we call these, or 0.1As that are 10 times fainter. Yep, we're geniuses. On the core collapse side, you've got type 2s, linear type 2s, plateau type 2s, narrow line type 2s. The 1Bs, you can have 1Bs with narrow lines. You can have 1Bs that start off looking like type 2s and then end up looking like 1Bs. You can have some which have lots of calcium in them that actually resemble more like type 1As. You have 1Cs, but 1Cs that have very, very broad lines in them. Broad lines mean high velocities, such high velocities that they can't be powered just by the core collapse of a supernova and lots of nickel, but also they must need some kind of central engine. So we have gamma ray burst supernovae here, where a star collapses to a black hole and the spinning accretion disk of a black hole launches a jet, or superluminous supernovae, which we believe are powered by the newly formed neutron star having extremely strong magnetic fields. We call that a magnetar, a strongly spinning magnetic neutron star, which somehow couples with the supernova ejector and sends that flying out and heats it up. And these things are all extremely new, extremely rare. We only have 100 superluminous supernovae and maybe 100 GRB supernovae. Calcium rich, we only have 20 or so. And so all of this, we all need to go back to my wonderful little circular diagrams and work out how everything on this page relates back to the stars that evolved to create them. How are we going to do that? This is where we point to the future. And in the next couple of years, we hope that the Vera Rubin Observatory, which has the Legacy Survey of Space and Time, or LSST, this extremely new large survey telescope in Chile. I said we currently have 30,000 confirmed supernovae. LSST is planning to discover 1 million, maybe up to several million. So in the next decade, the research area of supernovae will be pushed to yet another dimension, and we might find even more weird and wonderful things. On that note, I would like to thank you all for listening and welcome any questions if I have time.
Well, thank you very much, Phil. I think we have plenty of time, actually. We're running slightly ahead of schedule, so that won't be a problem. And Phil Wallace is going to read out questions and invite you to answer them.
Indeed. Good afternoon, everyone. Firstly, Dr. Wiseman, thank you very much. That was extremely interesting. We've got a couple in the Q&A, which more or less I have here. You had a plot, a whole sky plot of confirmed supernovae, and the question was, why were there some gaps? Because they look like very distinctive sort of ring-shaped gap where there weren't any at all, whilst the other areas of the sky seemed packed with the things.
That is a very good question. I'll just go back. So here, that's a very good question. This is a what we call an equatorial coordinate plot of the sky. So if you were in the middle, you'd be on the equator looking up at what we define as effectively the same as the Greenwich meridian, but in the sky. And this black unfilled patch is where the Milky Way is. So that's the plane of our own galaxy, which is so packed with stars, but in particular dust, that it's just too thick to see through. So we will never see a supernova. We think even on the other side of our own galaxy. Now, as I said earlier, the Neolithic and ancient astronomers said that supernovae they saw, which were in our galaxy, were bright enough to see in the daytime. But if one happened on the other side of our own Milky Way, through the center and on the other side, the dust would be so thick that we would never even see that supernova. So this is because this is our Milky Way and we just can't see through it.
Okay, that makes sense. I thought it might go. I've come across the terms zone of avoidance or so that's fascinating. Next up, we have a question from Darren J, who asks, "What do you think of Professor Chaplin's dark energy stars as opposed to black holes? Is that something you're familiar with at all?"
I must admit that I've never heard of a dark energy star. So I can't help you on that one. But I will say is, I mentioned the Dark Energy Survey that I'm part of, where we effectively are using supernovae to try and measure the effect dark energy has on the universe. And even with that, we're going to make the most precise measurement ever of the effect of dark energy. But even in that, with that, we have no idea what dark energy itself is. And so, sure, there's a chance you could conceivably have a star made of whatever it is, but I can't go any further.
Okay, thank you very much. As a sort of follow-up for that, John H asks, any evidence for the super bright, the super luminous supernovas you mentioned forming Prion stars? I must admit, I'm not sure quite what Prion stars are either.
Yeah, again, Prion is a term that is new to me. Maybe some of the others can jump in or enlighten me. We think, as I said, that superluminous supernovae. So in general, they're supernovae. We think they're caused by the rapid spin down of a newly formed magnetar or magnetic neutron star. So we think that the remnant of that will still be a magnetar. And there's a curious link in that another phenomenon that I haven't touched on here, which we call fast radio bursts, where you get a very extreme pulse of radiation in the radio frequencies, seem to be linked to magnetars. And so the idea is if you can see a fast radio burst from the same place that you saw a superluminous supernovae, you could convince yourself that maybe a magnetar was the central engine of this superluminous supernovae. But Prion stars are beyond me, I'm afraid.
Well, someone did just suggest in the chat that they might be stars with mad cow disease. How that would work, I don't know, and I'm not sure I want to find out. Next up, from Kyle Marston, asks, once you have spectrums of these millions of supernovas, are there any space oddities, and he specifically uses that term, I think he's a Bowie fan, that you haven't seen yet, but you've predicted that you're specifically looking for?
Oh, that's a really good question. So there are some that we think we might have seen one or two of. One good example, I think, Vivien and maybe Nils will touch on, is the collision of neutron stars. So I won't spoil it, but we like to predict what that might look like, and what the spectra of those will look like is very, very subjective, and lots of people have lots of different ideas. So we don't really know what they'll look like. Another one is an object which we have one example of, which exploded 3 years ago, and the designation AT 2018 COW, or cow. So all of the papers have lots of puns in them, which is brilliant. There are no convincing models as to what caused that. So it declined very, very fast, didn't seem compatible with nickel decay, may have had a black hole or a white dwarf black hole, some kind of orbiting or some kind of jets being created. That had quite a strange spectrum as well. And again, we don't know if lots more like that or lots more a bit similar to that might appear in LSST. Of course, the extreme challenge is that with so many, we won't be able to get a spectrum of all of them. So you have to choose which ones you point your spectrograph at, which means we have to write lots and lots of applications. And the second problem is that there's just not enough there's not enough human time, research time available for everybody to look at each of these spectra by eye. So you have to teach computers to find things, find the type 1As, find the type 2s, find the type 1BCs. And so the likelihood is that they find the weird things and they just throw them away because they say, oh, that's not what I'm looking for. So it's a real challenge trying to come up with plausible spectra and light curves for things that we don't know are going to be there, and training the computers to actually find them and set them aside for us to go and look at with our eyes.
Okay. Next, we have a question from Vincent Bryson, who says, awesome stuff, Dr. Wiseman. Were you disappointed when Betelgeuse erratic behavior a couple of years ago was attributed to merely dust and not an imminent explosion?
Yes. I was let's say I was pessimistic that it would trigger an imminent explosion. There are lots of things that can cause a star to dim, and so I was never excited that it might just suddenly explode. But we did have the discussions within our collaborations of what happens if something like Betelgeuse explodes. What's our strategy? The problem is that they would be far too bright for any of our telescopes. So we'd have to rely effectively on small and amateur astronomers to take the data because they would just destroy our detectors. Regarding dust, it just does allow me to say that almost every exciting or potentially exciting by it was just dust.
That sounds about right. That seems to be the universal explanation. It's either dust or magnetic fields, one of the
Correct.
two.
Yeah.
That actually leads on quite nicely to a question that I'm sorry, I'm trying to read this rather small font. Martin Willett asks, which is, can citizen science projects help with analysis of spectra?
Yes. There has been at least one. I think it was called the may have been called the Zwicky Chemical Factory or something. So one of these surveys you see on here, the bright pink or purple is ZTF, the Zwicky Transient Facility, named after Fritz Zwicky. And they have a few thousand, 5 to 10,000 spectra of supernovae. And again, they have not been able to look at them all by eye. So one thing you can do is you can create your model spectrum and then help get the citizen science to train your computer algorithms to classify those spectra. So citizen science going forward into the Vera Rubin Observatory era is going to be extremely important in training our models and detecting anomalies in the data.
That's certainly encouraging. I mean, I know it's said quite often that astronomy is about the only science left where amateurs can make significant contributions. And it's nice to know that is going to continue.
Yeah.
And then I think the last question we got in the Q&A from David Stott, who's joining us all the way from Glasgow, asks, where do elements heavier than iron come from?
So, wonderful question. I think some of that might be touched on in the next few talks. So that's a wonderful segue into that. But very briefly, I said that you can't fuse anything heavier than iron and nickel. So in this runaway thermonuclear explosion in the type 1A or in the core collapse, you can't do it with fusion, but you can do it by bombarding your, and so if you have a new neutron star, or if you have some high flux of neutrons from a new compact object, or because everything is extremely hot and dense, you can effectively just bombard your new heavy elements with neutrons. And you can do that in various different processes, and then some of those neutrons will decay into protons, and that will create some of the heavy elements. So most of them are produced in these explosions, type 1a or type 2, and that's how we get the things that we see here, like uranium and gold and silver and all of the heavy elements. So yeah, very good question.
So you really can turn iron into gold. The alchemists were right.
Yeah. I don't want to spoil anything, but I'll leave the gold until the for another talk.
Okay. Hang on a second. Right. We did have another question. Someone put it in the chat, so just give me a second.
Can I just, while Phil's looking, intervene to say, please could you not raise your hand, but please could you instead put your questions in the Q&A? Thank you very much.
Yes, thank you, Jane. Dr. Wiseman, that simulation you had of the type 1a, the exploding neutron star, that was fantastic. Where did you come up with that?
That simulation is on YouTube and is a good 10 years old now. Sadly, we don't have any kind of computational theorists on supernovae in Southampton, and I didn't want to go around bugging people for simulation, so I had a look on YouTube, and there are some on YouTube. They are extremely clever people who do these simulations of supernova explosions, because they include such extreme physics, hydrodynamics, radioactive chains that we can never ever see or model on Earth. So it's highly theoretical, and eventually they just run as many of these as they can with slightly tweaked conditions until they look a bit like what we see on the sky. But the type 1a models, as good as they are, I showed there were two different ways to forming one. You have one with a normal type red giant, or one with two white dwarfs. They'll explode in slightly different ways, but we still don't know which one is the right one, or if both or either can work. We still don't know. So we need these theorists to make better models.
The reason I asked about the simulation is I do a talk myself on a somewhat less technical scale, I admit, on the life cycle of stars. So if that's just free on YouTube, I may look at using that one. That's absolutely fascinating. Right, we have got another couple that have pinged in. This one is just from Anonymous, unfortunately, asking, so we don't think we'd see a supernova if a black hole is formed immediately instead of a neutron star?
Yeah, so the problem when it's complicated. The problem with forming a black hole is that means when the core collapses, or when the white dwarf collapses, you could say, but typically they would be for core collapse. When the core collapses, you need the neutron star to form for everything to bounce off, shock, and head back out again. You need somehow to turn all this falling energy into explosive outward energy. And so if you go beyond a neutron star into a black hole, it does nothing to stop all of this material just falling, accreting, and just becoming a black hole. And so we think that if you've become a black hole, you likely just the exception being a the gamma ray burst, where you have enough rotational energy that when you form like an accretion disk around the black hole and launch these jets, those jets blast out through the falling, collapsing star, and you get an extremely energetic explosion.
Okay, thank you. And then I think we've got last
we're out
two.
of time, I'm afraid, Phil.
Oh, okay. In that case, Dr. Wiseman, thank you very much. And I shall hand over back to Jane for the next session.
Thank you very much.